Hi, everybody. It's Professor Mitchell, continuing with Chapter 2. In this video, we'll look at Section 2.2 on general systems of linear equations. In this section, we'll look at pivoting a matrix. We'll continue with looking at the Gaussian elimination method. We will look at the situations where a system of equations has infinitely many solutions or is inconsistent. We will not look at the geometric representation of a system in this section. We will look at that later. All right, so pivoting a matrix is something that we did in the last section. We just didn't officially use that term. To pivot a matrix about a given non-zero entry, first we transform the given entry to a 1, and then transform all other entries in the same column into zeros using the elementary row operations that we talked about in the last section. So for our first example, we'll pivot the matrix about the circled element in this augmented matrix. So let's switch over to the tablet. All right, so we're pivoting the matrix about the element -6 in the first row, second column. So that means first transform that element into a 1, and we do that using elementary row operation number 2, which is to multiply a row by a non-zero number, in this case, -1/6. So that's going to make that first row 18 times -1/6 is -3. -6 times -1/6 is 1. That was the whole point. And 15 times -1/6 would be -15/6, which simplifies to -5/2. And we're leaving the second row alone just for now. All right, but to complete the pivot, we now need to make this -2 a 0. So we do that using elementary row operation number 3. We are going to change row 2 by adding to it 2 times row 1. All right, so at some point in the very near future, I'm going to try to wean you off this, but I will go ahead right now and just write down what is 2 times row 1. I'll put it up here, just so we have it to look at. 2 times -5/2 is -5. So we're going to add these two things together. And then we will have completed the pivot. So we're leaving the first row alone. Okay, and now the second row is going to become -6 plus 5, which is -1. 2 plus -2, which is 0. That was the whole point. And -5 plus 4, which is -1. Notice they're not asking us in this problem to solve the whole system. They just wanted us to get some practice with doing that one pivot. So that pivot is now complete. After doing that pivot, the augmented matrix looks like this. So I think the reason that they're introducing you to pivoting now and using that terminology for it is now we have some vocabulary that makes describing Gaussian elimination a little easier. So here's the problem we just did. Okay, so now let's describe Gaussian elimination in terms of pivoting. And remember, we use Gaussian elimination to transform a system of linear equations into diagonal form. So the first step is to write down the matrix corresponding to the linear system. Then we need to make sure that the first entry in the first column is non-zero. We do that using elementary row operation number 1, which is to interchange that row with one of the rows below it. This is usually not necessary. Usually that first entry, first column is non-zero, but once in a while it's 0. So whenever that happens, just swap it with another row. All right, so once you have a non-zero entry in that first row, first column, you're going to pivot about that first entry, which means make it a 1 and make all the other entries in that column 0. Okay, now we're going to do the same kind of thing with the second column. Make sure that the second entry in the second column is non-zero. Do this by interchanging the second row with one of the rows below it. Okay, not with the first row, because we don't want to mess up that first column. Pivot the matrix about the second entry in the second column, again, which means make that entry a 1, make every other entry in that column 0. Continue in this manner until the left side of the matrix is in diagonal form. And then write the system of linear equations corresponding to the matrix. So in the case of a unique solution, which is what we looked at in the last section, at this point, you'll write down something like x equals 4, y equals 1, z equals -2. But we're also going to talk about the situation in this section where your system does not have a unique solution. All right, so one way that can happen is if your system has infinitely many solutions. When a linear system cannot be completely diagonalized, apply the Gaussian elimination method to as many columns as possible. Proceed from left to right, but do not disturb columns that have already been put into proper form. As much as possible, each row should have a 1 in its leftmost non-zero entry. Such a 1 is called a leading 1. The column for each leading 1 should be to the right of the columns for the leading ones in the rows above it. And this will make a lot more sense when you see an example. So don't panic. Variables corresponding to columns not in proper form can assume any value. The other variables can be expressed in terms of the variables in step 2. This will give the general form of the solution. So you'll see what I'm talking about here in just a minute. As we look at this example, we're going to find all solutions of the system 2x plus 2y plus 4z equals 8, x minus y plus 2z equals 2, and negative x plus 5y minus 2z equals 2. So I'm going to start by switching over to the tablet where I have already written down the augmented matrix that represents this system. And you can see that system here. All right, so let's do the process that we have started talking about. So the first thing I need to do is pivot about the first row, first column, this 2 here. So we need to make that a 1. And the way that I do that is by multiplying that row by 1/2. Okay, so that first row is going to become 1, 1, 2, 4. And then the next thing I'm going to do is, you see the 1 and the -1 underneath that circled 2. I'm going to make those zeros. All right, so let's start with the second row. We need to change the second row by adding to it -1 times row 1. And if you prefer, you can just think of that as row 2 minus row 1. Makes it easy to do in your head. So we're not changing row 1 right now. However, row 2 is going to become this row minus this row. So 1 minus 1 is 0. -1 minus 1 is -2. 2 minus 2 is 0. 2 minus 4 is -2. And then I'm going to change row 3 by just adding to it row 1. I mentioned to you once in the last section, I love when I'm trying to get rid of a -1 because usually it just means adding it to the pivot row. So now we're doing this plus this. -1 plus 1 is 0. 5 plus 1 is 6. -2 plus 2 is 0. 2 plus 4 is 6. All right, so we've done what we needed to do with the first column. So now we'll continue with the second column. All right, so now we're ready to pivot about the -2 that you see here. So the first step is to multiply that row by -1/2. We're not doing anything to row 1 just yet. 1, 1, 2, 4. However, row 2 will become 0, 1, 0, 1. And we're not doing anything to row 3 just yet. 0, 6, 0, 6. Okay, but now we need to get rid of this 1 and this 6. So we do that using elementary row operation number 3. First, we need to change row 1, and we're going to change row 1 by adding to it -1 times row 2, or if you prefer, just row 1 minus row 2. So the new row 1 will be 1 minus 0, which is 1. 1 minus 1 is 0. That was the whole point. 2 minus 0 is 2. 4 minus 1 is 3. Oops. Goes there. We're not doing anything to row 2. Okay, now here's where something interesting happens. We need to get rid of the 6. So we're going to change row 3 by adding to it -6 times row 2. All right, let's try to do this without scribbling in the fake unofficial row. So row 3 plus -6 times row 2. This row plus -6 times this row. 0 plus -6 times 0 is 0. 6 plus -6 times 1 is 0. That was the whole point. 0 plus -6 times 0 is 0. And 6 plus -6 times 1 is 0. So at this point, normally we would work on the Z column, right? But I'm not going to be able to do that because I have a 0 right here. And I don't have any more rows underneath that row that I can swap with that row, okay? So at this point, we just write down the system that our augmented matrix represents. X plus 2z equals 3. And the second row says y equals 1. So the way that we write the solution is we say that z can represent any real number. Let me see if I can squeeze this in here. Z is any real number. Y is always going to be 1. And then the x equation, just solve that for x. So you see how it says x plus 2z equals 3. Just subtract 2z from both sides. And that will allow you to describe x in terms of z. So it would say x equals 3 minus 2z. Okay. So that gives you a nice convenient way where you can, this is a description of all the solutions. So make z any number you want. Y will always be 1, and then x will always be 3 minus 2z. So for example, if z is 0, that would mean x is 3. If z is 10, then x would be 3 minus 2 times 10, which is -17. So you get an infinite number of solutions, and this gives you a nice, easy way to generate all those solutions. All right, so let's go back to the presentation. And this should all look familiar. All right. Okay, so the other situation that can happen when your system does not have a unique solution is that it has no solution at all. When using the Gaussian elimination method, if a row of zeros occurs to the left of the vertical line and a non-zero number is to the right of the vertical line in the same row, then the system has no solution and is said to be inconsistent. Okay, so when we do the example, you'll see why that means the no solution. Okay, it'll make perfect sense. All right, so here's the example. We're going to try to find all solutions of x minus y plus z equals 3, x plus y minus z equals 5, and negative 2x plus 4y minus 4z equals 1. So once again, when I switch over to the tablet, you will see the augmented matrix that represents this system. And we will go about the business of Gaussian elimination. So we'll start pivoting and putting this thing in diagonal form. So notice that in the first row, first column, we already have a 1. Okay. This is the point where if you had some other number there, you would make it a 1. Okay. So we can skip that step and just go right to the part where we make these numbers zeros. So the first thing we need to do is change row 2. We're going to change row 2 by adding to it -1 times row 1. Or if you prefer, just think of that as row 2 minus row 1. Keeping row 1 just the way it is. The new row 2 will be 1 minus 1 is 0. 1 minus -1 is 2. -1 minus 1 is -2. 5 minus 3 is 2. All right, and we also need to change row 3. We're going to change row 3 by adding to it 2 times row 1. Okay. So this plus 2 times this. -2 plus 2 times 1 is 0. That was the whole point. 4 plus 2 times -1 is 4 plus -2, which is 2. -4 plus 2 times 1 is -4 plus 2, which is -2. And 1 plus 2 times 3 is 1 plus 6, which is 7. And you might be able to see where this is going. Okay, so we're all done with the first column. Now we need to pivot about the 2. You can see right here. So the first step is to multiply that row by 1/2. Not changing row 1. Okay, but we are changing row 2. We're multiplying it by 1/2. So that's going to be 0, 1, -1, 1. Not changing row 3 just yet. Okay, so now we need to make these numbers 1s. All right, so first we will get rid of this -1. You need to change row 1 by adding to it row 2. That's nice and simple. So our new row 1 will be 1 plus 0 is 1. -1 plus 1 is 0. That was the whole point. 1 plus -1 is 0. And 3 plus 1 is 4. Okay. Like row 2, just the way it is for now. And now let's talk about row 3. We need to get rid of a 2, so we're going to change row 3 by adding to it -2 times row 2. So this plus -2 times this. 0 plus -2 times 0 is 0. 2 plus -2 times 1 is 0. That was the whole point. And then -2 plus -2 times -1 is -2 plus 2, which is 0. And then 7 plus -2 times 1 is 7 plus -2, which is 5. All right, and now we are stuck. We can't do anything else in terms of diagonalizing this matrix. For the same reason that we got stuck in the last example, there are no more rows underneath this third row that I could swap to put a non-zero number here. So let's write down the system that this matrix represents. The first row says x equals 4. The second row says y minus z equals 1. No problem so far. But let's think about what that third row says. It says 0x plus 0y plus 0z. In other words, 0 equals 5. And at this point, I always think about my high school math teacher who would look at something like 0 equals 5, and he would say, liar, liar, pants on fire, which I have updated for the 21st century by making it a hashtag. All right. So 0 equals 5, that's something that can't happen in this life. So that means that this system has no solution. It is an inconsistent system. All right, coming back to the presentation. This all looks familiar. All right. And that's actually going to just about do it for section 2.2. So if you would like to grab either one of these problems for the discussion, if you're in my class, feel free to do one of these. So the summary of this section is that the process of pivoting on a specific entry of a matrix is to apply a sequence of elementary row operations so that the specific entry becomes 1 and the other entries in its column become 0. To apply the Gaussian elimination method, proceed from left to right and perform pivots on as many columns to the left of the vertical line as possible, with the specific entries for the pivots coming from different rows. After an augmented matrix has been completely reduced with the Gaussian elimination method, all the solutions to the corresponding system of linear equations can be obtained. So in the case of all the problems from section 2.1, you get a unique solution. And in many of the problems in this section, you will get either infinitely many solutions or no solution. If the reduced augmented matrix has a 1 in every column to the left of the vertical line, then there is a unique solution. If one row of the reduced augmented matrix has the form all zeros to the left of the vertical line and then a non-zero number to the right, then there is no solution. Otherwise, there are infinitely many solutions. In this case, variables corresponding to columns that have not been pivoted can assume any values, and the values of the other variables can be expressed in terms of those variables. And that's going to do it for section 2.2. We'll see you next time.